Hi, and welcome to this week's Background Fundamentals. Well, I'm going to swing back and do some more stuff on smaller companies, this whole idea of things that you can do in the changing nature of the industry later in the term, because I had a question about it in the forums. But this week I'm going to be doing something else, another question from the forums that came up about how can we get stuff accurate from on set. And I've done a few classes about how to do HDRs and how to do surveys and stuff, but one of the areas that we haven't done much on recently, I don't think, is having a look at lights, and in particular how to match those lights and some of the characteristics of them that make you understand why they don't perform perhaps the way that you think they would from a technical point of view. And I was very lucky to have a chance to spend a day or two with Dito, the guy who literally founded the company Dito. He was out here with LEMAC and he was giving master classes. I managed to do those with him. I also got to spend some time with him. I did a sit-down interview with him, and that will be coming out later on FX Guide TV. But I wanted to go technical right now with you guys because, of course, that's what we like to do in background. And I think this is some really interesting tech about what's going on. Certainly really clarified some of my own thinking. So when we're on set, what we want to be basically able to do is we want to sort of play with lights, right? Because we're trying to film light. Everything we get in front of the camera is, of course, after all, just bounced light. We want to film it, we want to copy it, we want to emulate it, we want to do a whole bunch of things. We also need to measure it, and we need to often match it. And this is where it becomes really interesting, because light is phenomenally interesting stuff. And to help us with that, there's a thing called the CRI, and that's the Colour Reproduction Index. And this is basically how light will handle, or how colours will be rendered in different lights. How well does a light render colour? How faithful is it? How does that happen? And so the way you would do that, of course, obviously, is you'd get some colours and you'd put some light on them and you'd test how accurately that comes up. And that's what they do. In fact, researchers use daylight as the benchmark for doing that, and then they compare a bunch of colours which are defined, and that tells you how good the lights are at allowing you to reproduce those colours. Now, this is a big difference between just intensity of colour. So I'm going to come back to sort of some of the other points, but let's start with our first sort of base, I guess, what is like our considered perfect light. And here, the benchmark, the 100 on the index, the thing that everything else is judged by, is sunlight. So we have, on a good day with good sunlight, you have a particular quality of light, and sunlight does almost everything we want it to do, and certainly whatever it does that's maybe weird and wonderful, it's what we accept as normal. So that's our benchmark. Whatever sunlight does, that's it. That's our baseline. Now, of course, obviously there's different times of day, different pollution levels, different whole lot of things that are going to cause sunlight or daylight to vary tremendously in colour. But we can define an actual daylight as a single kind of thing, and we'll set a particular temperature for it, which means that we're setting, in one respect, it's a sort of a precision, a nature of what is white light. We all know that from like dialing up on cameras, daylight, versus tungsten. But there are lots of ways you can think about this. In fact, sort of like a really interesting way to think about it is if you heat up a dark object to these various temperatures, this is the colour they will shine. So we'll come back to that, but like literally there are lights that we'll refer to as being 2600 Kelvin because they actually run at about 2600 degrees. But daylight is about 5600. Okay, and we're going to define it accurately down as our baseline and then measure everything else from it. And the reason for it is this: in the world of doing stuff, and we've been touching on this over at the DOP course, you're going to do HDRs. Here are a couple of HDRs I've done here. And the top one is in daylight, though you can see there are large sections that are a building that are left and right that are kind of obscured. And that seems like the colours look right just to my eye. Down below, however, is a car park. And in that car park, it looks kind of weird, right? There seems to be a fluorescent light that's going kind of red, and then there's also seems to be kind of a greenish tinge to the car park, and yet I can see in the distance that there's daylight coming in. Like, is the concrete green? Where's that sort of coming from? And if I was to do an HDR and measure this, I would be sampling all of the intensity of light hitting the point where the 360 degree is being reconstructed from. So I have my camera, I do my bracketed sets, but at that point it's measuring light from everything. It's measuring light from direct lights, measuring bounce light, and it's measuring the colours that are hitting it. But what it's not telling you very well is the actual colour space, or the sort of native colour that you should be looking at that in, because obviously in most HDRs we're shooting raw, and so for a start you don't even have a colour space applied in the camera. I'm putting it together in a program like PTI GUI, and at no point do I specify a colour temperature there, and then I output this HDR, which is mathematically really accurate. I've got, in this case, about 10 or 12 stops, bracketed shots, 10 bracketed shots either side, and each one of those CR2 files from the Canon camera is about 2 stops latitude. So there's a ton of kind of information that's gone into that. It's a huge file, 7,000 pixels across and about 3,000 pixels down. So there's no sort of lack of detail. There's no lack of sharpness. There's certainly no lack of light range. But what there is nothing to specify colour. So what we tend to do is we put a Macbeth chart in. Put a Macbeth chart visible when we're taking the HDR, and then what we can do later is say, okay, well, here's the Macbeth chart, and I can actually see now these colours. And these aren't arbitrary colours, these are really standard colours as defined. And that Macbeth chart we'll keep in a safe place, we'll keep it out of the sun, we'll look after it, and we'll even replace it every few years because the colours may fade. But these colours are colours that we know what the proportion of the mix of the additive colours are to get them. And also, these were printed in incredible accuracy. So that's great. That's got my Macbeth chart. Macbeth chart gets me most of the way there, but it still doesn't get me quite all the way there, because what's really interesting is that these colours under daylight can be measured, and we've got that as a good kind of base. But these colours under some other light, let's take this LED for a second. If I'm lighting this under this LED, there are two things that are going to happen. Firstly, the quality of this light is much more complex than can be defined in just simply its colour temperature, or even its colour temperature and tint, which in fact is what we normally do. When we hit up colour temperature, those are the two controls. What the temperature is, and then a tint offset. So you might have 5600 Kelvin and -7, -7 being your tint. Okay, that's only still not quite all the way there. I've now got accurate colours. I theoretically know what the colour temperature of this is, though it's not a very precise way of defining that light. But the other problem I've got is the actual cameras themselves, because the cameras themselves are not recording this sort of magically. They have filters that sit in front of the CMOS. And each of those filters is either green or blue or red. And so you're going to be filtering the coloured light, because I'm assuming that even if it's meant to be white, it's got some actual colours. And you're going to be filtering that by what's bouncing off my Macbeth chart and how those are interacting with the individual sensors. And so you actually get some really interesting results. You get some particularly interesting results of this baby, which is an LED light, which I'll come to later. But as LEDs are growing so enormously in production use, in fact, some companies, even away from our industry, have just stopped making like compact fluoros and stuff and are just making LEDs now. So we're going to be shooting increasingly more under LED light than almost anything else. These LEDs have some really peculiar properties that even push kind of the bounds of what you'd normally consider to be good models, such as CRI, for working out what's going on. And as I say, on top of all of that, individual sensors, like the sensor in the Canon, will react differently than the sensor in the Epic, which I'll show you in 1 second. So let's see if we can work our way towards understanding what's going on. And the first of that is the CRI, as I said. And the CRI, you take this, this idea of defining some colours. So we've defined white light. We need to define these colours, and that are a bunch of definitions. And the definitions are based on this kind of elaborate Munsell colour scheme on the right here. And what you can see is as you go up and down between black and white, you're setting a like a grayscale. As you move out from that column, you're setting a sort of a level of chroma or sort of saturation. And then as you go around the chroma wheel, you get sort of, luminance, hue, and chrominance, and you can define in those 3 dimensions these sets of colours. Okay, so that's how I define these colours. And on the left, these are the colours that are primarily used for doing the CRI. And that is a reasonable set of colours, but it isn't actually a brilliant set of colours. It used to be a lot more helpful than it is today. The ones on the right, these are colours that are really not included in the CRI calculation, though in some later or newer definitions that are being proposed for standards, they are coming in. And the one I want you to keep an eye on, because we're going to come back to it later, is this strong red. And I'll give you a heads up why, because if you've been shooting with LEDs, you might notice that things are coming out green, but the light is meant to be, say, daylight. And so why is it coming out green? Well, this would be the reason. It's an absence of red, which is number 9. But I'll come back to that in 1 second. Let's work our way through normal light so we can get some idea what's going on. Keeping in mind, as I say, that the CRI, while fairly good and used to be really terrific before we had things like LEDs, doesn't actually work very well on some new modern lights. In particular, any kind of light that has a spiky emission, in other words, over the spectrum of colours, it has these kind of super spikes or dips. And that's particularly the case with LEDs, as I'll show you in 1 second. Okay, so our light sources. So kicking in at about 98 is a halogen light. This is a great, 20 lumens per watt light. This is basically a filament that burns hot. And the thing about halogen lights is that you can run them as a low wattage. So as we have here, there's a low watt halogen, or you can run it as a high wattage halogen. But halogen actually, the actual thing, halogen, will melt at about 36,000 degrees. So you only get them in tungsten. They don't actually go to daylight. HMIs, on the other hand, being gas discharge, do actually run to daylight temperatures. So you get in HMIs about 80 lumens per watt. Now, the lumens per watt is like at the light source, not what's going out the front of it, because a lot of these things sit behind lenses, like a Fresnel lens, with reflectors at the back. So when I quote these numbers here about the amount of lumens that are coming out per watt, don't be confused as to the sort of actual strength of the light in front of it. It's just the light that would be theoretically generated. How much of that you capture through lenses and curved mirrors behind the light, depending on the brand of light you buy. Okay, and then we've got, with the HMI, we've got the ability to go down to tungsten as well, so both options. Obviously we don't go the other way because we can't burn the halogen that hot. And then we have fluorescence, and then fluorescence in an office environment would tend to be actually about 4,300, and you can get them in sort of daylight or tungsten, and that's fine, and they burn pretty well, and most people know that fluoros are quite bright. In fact, what we'll be talking about is these, which are Kinoflows, and Kinoflows are literally a brand of fluorescent, but the thing about Kinoflows, they are a brand, is that, to my money, there is no one that holds a candle, foot candle, nobody that can match Kinoflows for making really high quality fluorescence. And in fact, a Kinoflow has a much higher quality level than a normal household one. So you can see here, the CRI is at 75 on a normal household fluoro, but if you buy a Kinoflow, either tungsten or daylight, you're getting something way up at 93. Anything in the 90s is really stellar. LEDs have probably the most variation. You're going to get anything from about 75. In fact, you can actually get them in torches down at like way lower than that. But in a light you would buy, you get anything from about 75 up to about, if a really good one, a really professional top-of-the-line LED light, you're going to get something up about 92. And the biggest takeout from this stage so far in the lecture has to be that all LEDs are not made equal. There's a really vast difference. To give you an idea on that scale, I've just set this up with this sort of like English version of the numbers, I guess is the best way to describe it. As I said, anything in the 90s we'll call accurate. That'd be really good for doing lighting in a museum or in a art gallery, that kind of thing, or studio lighting. Anything that you really care about it in the 90s. If you're in the 80s, well, that's pretty good. That's okay. If you're doing good retail setup, somewhere where you cared about colour because you're selling stuff, but it's not like in a studio professional environment. At 70 to 79, you're down in kind of supermarket level, which is why supermarkets have fluoros, or why fluoros cause supermarkets to only rate that highly. If you go much below that into the 60s, you're into basically warehouse. And when you get below that, down into the 40s and 50s, you're talking about the sort of stuff that's in car parks, like, underground car parks where you park your car, or security kind of areas, or emergency lighting, stuff that absolutely would never consider in any way, shape or form to be anything particularly good. And as I say, if you can get good quality stuff, especially new high quality LEDs, you can get stuff up in the 90s, though it's not easy, but you can do it. HMIs, halogen, and of course sunlight are all valid things. Now, this is the reason why LEDs are so variable. And this diagram basically is one that we got from Dito. And it's about the binning process for making LEDs. Now, the way that LEDs are made is quite hit and miss. You can't actually make each LED to a particular specification. What you do is you make just gazillions of them, and then you rate them all in where they are in terms of quality, in terms of colour, and put them into the appropriate bin. So all these little grids that you see here across this spectrum around the the colour temperature line on a chromatic diagram, these are all sort of, I guess, deviations from what you want as perfect. And so what happens is you'll get some that are really great, right? And you'll get some that are junk. So the junk ones you throw into the outer lying bins, and the really good ones are sitting in the middle. So the yield on the really, really good ones is relatively small. Of course, because there's a lot of area around the outside, you get quite a lot of low quality ones. You sell the low quality ones for lower cost lighting, and then you try and get the really high quality ones for big, big professional lights. But that's why they're, even from the same factory, from the same batch, you can buy much more expensive LEDs or cheaper ones. It isn't that if they come from this supplier or this country, like that the German LEDs, they're really good. That makes no sense. Any factory on any day is producing good and bad ones. You just have to get the pick of the crop. And you might point out, if you were clever and liked maths a lot, that if I've got an array of these, couldn't I kind of have them average out? And to a certain extent that's true. Some light manufacturers that make moderate quality LED lights try and do that. They try and not buy the most expensive LEDs, but they buy a range and hope that if they get the mix right, on the law of averages, if there are enough LEDs, the bad ones will cancel out with the good ones. The trouble with that is it adds to the inconsistency of the light, but it is a possible technique that some people use, but you wouldn't really want to go there. Minor amounts of averaging from associated bins is always probably going to happen, but yeah, massive amounts of averaging, it just doesn't work out very well. And of course the whole average can shift way off beam. There's no guarantees. There's one other big problem with LED lighting, which is us, because my eye isn't very good at picking up on some of these things. And so what you're going to see, and we've found this ourselves, is that you can look at an LED light, you can do all the right things, you can put a scrim on it and sort of, so you're obviously averaging it out and you're making it kind of and you look at the light with your own eye and you say, well, that looks about right, it looks kind of the same as these other lights. But as you can see in this, for a while we've known that we aren't actually very good at picking between colours. Well, we've known this here in PhD, we've referred to it many times, that if you're going to get something right on a camera, you want to get the sharpness in the black and white, but if the colour is a bit off, your eye isn't very, isn't very fussy to just colour. But this is actually how unfussy we are. You can see up in the green, anything inside one of those ellipses, those ovals, I couldn't tell the difference. That would be, you could show me two different reds or two different yellows or whatever from inside any one of these ellipses, and I wouldn't be able to pick the difference between the colours. Assuming, of course, that I'm not changing the light level and making them lighter or darker, just in terms of colour. Pretty big band, especially around the colour temperature. I just can't pick it with my eye. You can't pick it. It's just really hard for us with our eyes to do it. And yet, those variations will make a difference between multiple lights and also make a variation when it hits the sensor. So, how different are these two colours is like a really hard thing for you to answer with your eye. So what we're going to do now is we're going to find our way of checking stuff that you can do that's really relatively easy. Because we've got these Macbeth charts, and because we've got a couple of different cameras, a Canon and an Epic here, what we're going to do is we're going to film this chart, and we're going to film it with, theoretically, daylight coming from a couple of different sources. And then what we'll do is we can mix and show you the same colours, 50-50 split between what's coming off two lights, both projecting on the same chart, and then composite it together in post. In other words, film it once under, say, LED daylight and once under, say, Kinoflow daylight, and then split screen the results to see if you can notice a difference. And the next thing we're going to do is actually just see if we can tell that on a single person. We'll actually set up lights on someone, maybe me, and put them on either side and see if we can actually tell the difference to our eye once it's coming back through the sensor. So let's do that now. Okay, well, this is our setup for filming our test chart. So you can see it here. This is with the Kinoflow up. This is the large LED panel up, and you can see here both the Epic and the Canon. We're looking at the Epic first, and then just to show you, there's the small LED. We obviously sort of move things in to try and indicate or keep, I guess, the same kind of constant exposure on the panel. And yeah, you can see here, this is the sort of wide shot of what we were basically trying to achieve. Okay, so this is where we are. Let's have a look at the results. And what I'm going to start first with is the daylight. So let's look at the daylight Keener flow. Now this is the Keener flow in an epic environment, and in that epic environment we are shooting daylight. So daylight, Keener flow, that's our gold standard at the top, and underneath is the ARRI 650 with CTB. Now these are a pretty good match, so you can see here there's obviously sort of some differences, but generally speaking, in terms of colour now, if you look at the range of colours, they match pretty well, right? You've got a daylight, proper gold standard at the top in each case, here and here, and then the next layer down you have the ARRI with its correcting CTB, and not unsurprisingly between both companies, which are ARRI and Keener flow, you get really good results and they match. And that's what we'd expect. I mean, there's going to be some minor differences, but that's okay. They're a really, really good match, especially when you consider that ARRI is going through a piece of filter, and we haven't scrimped on the filters. All right, well, let's look at our other tests then. So we're going to start with looking at the Keener flow, again on the top, across here, and now we're looking at the large LED, which we're calling the 1.5 foot or the half-foot LED. And you can see here now in the browns there's a difference. You can really see a difference here in what's R9, which is the reds. But I'm seeing differences in the yellows. This is a really sort of more mustardy yellow difference. I'm seeing some tint in the LED down the bottom. You see there's a kind of a greenish sort of look to the grayscale. But yeah, across the board I'm seeing significant colour differences, way more than I was seeing between the ARRI and the Keener flow. Okay, so let's stay with that daylight Keener flow, and let's go to the small LED. So this is like a baby LED, the one you'd put on top of a monitor kind of thing. And here again we're seeing big shifts in colour, especially look how burgundy red that R9 has gone. But we're seeing that redness affected our purples and our oranges. Look at this, there's a real green tinge in this orange over here. And yeah, so the only thing that's changing here is that we're putting up an LED versus our gold, and the LED is a daylight LED. It's, you know, meant to be doing exactly what we're expecting. All right, now let's look at the most expensive LED we have, which is the Z90. So this is the Z90, and again along the top is the Keener flow daylight, and down the bottom is the Z90, and I'm reading like real pink in the Z90, even though this has got an electronic ballast on it that's theoretically, you know, dialing up exactly the right color temperature. I mean, look at these yellows here, big difference in R9 in the reds, just chalk and cheese. And it's funny, perceptively to your eye, this may look like the whole thing is really, really desaturated, but in fact we haven't touched the daylight in every case. It's the same file along the top. We're only ever changing the bottom. So there is perceptual differences happening because of the nature of what's changing along the bottom. But I can assure you, and you can check it out if you want, if we jump back to, say, the large LED versus the daylight, they are in fact not changing, but it just looks like they're changing because the bottom half of each square is changing. Okay, so that's our daylight comparison. Let's now look at our first tungsten comparison. And what I'm going to do is look at the tungsten. And now we know that the gold standard is the tungsten 650 from ARRI, because that's an untreated ARRI light. It's great. So we're going to match that up. And I know that the Keener flows are going to work. So what we've done is we've stuck in those 29 tubes. These are the third type of tubes that Keener flow make. They make the white, that is basically daylight. They make the tungsten effectively, and then they make the 29. So that would be the 55, the 32, and the 29. So these are the 29 tubes. And I just want you to see that there is a difference with the 29 tubes. Though the differences are, you know, smaller, I can see a difference here between these two greens. And I can, sorry, between these two oranges, but I can see it in the blues. This is kind of definitely more purpley than this, and although the greys just aren't matching quite the same. So there is a difference if you decide to use the Keener 29s versus the 32s, which I thought there wouldn't actually be much difference in. Okay, let's now look at the LEDs. So we're going to now compare the tungsten with a range of LED options, and the first of those I want to look at is looking at it with the Z90. Okay, so there's the Z90 now dialed into tungsten, and we haven't changed the top. So gold standard is the 650, below is the Z90, and wow, I mean, look at that in R9, this purpley pink difference, the I mean, it's just differences right across the board. It's like a big difference with the Xi 90 when it's dialed up into tungsten mode. And this is, you know, meant to be a really good LED light. Okay, so let's now look at the, I guess, the small baby LED. So this is the smallest LED we have. It's theoretically the cheapest LED we had, and it's got a real green tinge that's coming up. So this small LED has to be actually filtered. They have to actually put, you know, a filter in front of it to make it go from daylight to tungsten. So you may argue that maybe we've got the wrong filter, but that is as maybe. The fact of the matter is that we are using exactly what you meant to do to convert daylight to tungsten. So if you put up a normal filter, which is what a gaffer might reasonably grab, you're going to get huge differences. I mean, this is red and orange now in R9. And this isn't just explained by the filter, it's explained by the fact that the spiking frequencies in the LED are really apparent in this super cheap LED. So let's now go to the sensible larger half foot. So we're going to be on tungsten, and we're going to compare that to the half or the large LED. So this is the large panel LEDs, and we're now again having to filter that large panel LED to make it match our gold standard, which is the ARRI 950. And yeah, I mean, you know, we're seeing big differences. Again, this red to this red to sort of effectively orange difference down here is just extreme. Now, the question is, you know, could you color balance this out by just tweaking it in the grade? And you could get some of the way there, but the important point about showing this is that this is not a uniform thing overall. You see how this looks, the blues look desaturated here, the reds look significantly shifted. Like, this isn't just going to be done by one simple color correction. It is in fact changing across the spectral range. But this is all looking at test charts, and I'm always nervous about looking at just test charts. So what I'm going to do now is actually take this setup. I'm going to take the ARRI 650 tungsten, which is our gold standard, and I'm going to light my head, or rather get Jim to, with that on one side of my face. On the other side, I'm going to get the high quality LED large area light and then punch that in on the other. So we're going to compare these two, not on some, you know, test chart, but on me in our studio environment. But we'll try and make it so that each light doesn't contaminate the other. But strictly speaking, this is what matters, right? What does it look like on people? Can you actually tell the difference on a person versus a test chart? Okay, well, here's the proof. And as I'm often tending to say, my father once said to me, you can read the entire works of Sigmund Freud, but sooner or later you've got to take a girl out on a date. So here we are with what's theoretically the camera's set to tungsten. We've tried to, with a light meter, balance my light level on right and left. And in both cases, they should be tungsten. They should be identical. But on this side, your camera left, we have the gold standard of tungsten, which is an ARRI 650 light. So it's a full ARRI brand, proper tungsten light. That's our gold standard. On this side, we have an LED, which is clearly not the same. Even though it's gelled up, specced up, and is meant to be identical, clearly on my face, we can see a noticeable difference. Yet if you hadn't looked at this test, if you just asked me and said, hey, you know, I need to have tungsten, I'd say, okay, well, I'll just tungsten this light or tungsten that light, they'll match. Well, clearly they don't. Let's have a look now in the daylight. And I should point out, these first tests, the ones you're looking at right now, are all through the sensor that's in the EPIC, the MX sensor. Okay, so now what we've done is we've switched to daylight. So we've switched the camera to daylight. We've tried to now balance up daylight on this side with the Kinoflow. This is Kinoflow with the Kinoflow tubes in it, which is our gold standard, the best we have for daylight, this side of actual daylight. And it's coming in on this side, so that's our gold standard. On this side, we have the Z90, which is the most expensive LED we have here in the studio at the moment. Now, the Z90 actually can be programmed for any color temperature. It has a proper control on the back. We're not sort of, you know, guessing that it's daylight. It actually has full electronic controls, ballast. It's a proper expensive LED, and yet the two daylights still don't match. But this is all on the EPIC. So what we want to do now is take this exact same setup, which is the daylight and the daylight, the Z90 and the Kinoflow, change nothing but the camera, and see if this setup, with nothing changing at my side, changes if we switch cameras. Okay, so I haven't changed anything on this side. We've simply swapped cameras. So you're now seeing me coming from a Canon 5D Mark III. So the difference you're seeing in terms of how the LED is responding is how the sensor is responding to the light that it's getting. Now, it should be I imagine from what I've seen in the test charts, it should be not as pink as what we were seeing off the Epic. This isn't a fault with the Epic, it isn't a fault with the 5D, it's just the fact that the LEDs interact differently with the actual CMOS chips. Now, just to be really clear for those of you that are mega technical, the camera that is the Epic is recording RAW, of course. The camera that is the Canon is having to record in a codec. So what we've decided to do is record it as you do inside the Canon camera as an H.264, but we're recording it with the Cine style, which is Technicolor's effectively kind of log, very flat profile. And the reason we're doing that is we're not inheriting any kind of color space stuff that's being applied to make the picture look good. If you're recording this just in one of the normal picture modes on the Canon, you might argue that some of that effect is coming from the way the Canon does the compression. Well, it isn't. It's as neutral as we can possibly get on the Canon 5D Mark III. It's just the CMOS chip handles the LED's spiky frequency differently than the Epic does, and neither one is right or wrong, but isn't it interesting that they're not the same? And I can even prove that even further by jumping back to the Epic, back to the 5D, back to the Epic, and if that's not enough, let's split screen my face. So I now have still the Kinoflow on this side, still the daylight Z90 on that side, but now the top of my face up here is Canon 5D, and down here is the Epic footage. All right, well, enough of that. Let's now jump to looking at the Canon and how it responds to the LEDs when running in tungsten mode. And this time what I'm going to do is I'm not going to go back to that earlier gelled up light. I'm actually going to punch up tungsten on the Z90 for a comparison. Okay, so all we've done is dial in now on the digital display, the controller for the Z90 tungsten, and switched on this side, your camera left, from what was the Kinoflow daylight to the ARRI 650 tungsten. So we've got our gold standard tungsten on this side, Z90 LED on this side, and they should be equal. And that's what it says in the textbook. But what you're seeing, of course, is this response of the spiky frequencies of the LED now through a CMOS chip in the Canon 5D, which is actually a very different CMOS chip than the Epic MX chip. Well, look, I'm not a huge fan of test charts, but I think it's really easy to see these differences on those test charts. We looked earlier at the test chart comparisons A and B with the Epic sensor. Let's have a quick look now at these lights and a test chart, a Macbeth chart, but all on the Canon 5D Mark III CMOS chip. Okay, so here's what we just saw, the ARRI, which was on the left, the gold standard, versus the programmed in tungsten on the Z90. So this should be, as accurate a tungsten LED as we're going to get, and we can see a huge difference here. And I just want to point out that some of these differences would seem really hard to grade out. Look at the increase in saturation, it appears in red, versus a decreased saturation in the yellow. Like these just seem to be chasing each other, right? If I try to increase the saturation or decrease it here, I guess, in the Z90 to match the ARRI there, I'd be having to go the other way in the yellows. Greens, blues, it's really actually quite marked in these oranges. Okay, so let's look at some of the other tungsten results. Of course, all of these are now on the 5D sensor. So let's have a look at the tungsten versus the small LED. This is the small LED. This is the cheapest LED we had. It's now got a filter over it, and so yeah, it's really out of whack. So getting a cheap LED and putting a filter on it is almost guaranteed to get you into all sorts of strife in terms of matching up into color balance. I mean, it really is quite a mess. I'm going to show you this one. This is the tungsten 650 versus the Kinoflow, but not the tungsten Kinoflow lenses. These are the 29s versus the 32s, because I just want to show you that there is in fact a difference in running the 29s over the 32s. If I go to like matching like for like, let's do that with this. This is what we saw as almost a near perfect match in the Epic, which was the daylight Kinoflows with the ARRI with the correct CTB or color temperature balanced filters. And yeah, I think here there's a little bit of a luminance difference. It almost seems like it seems a little brighter at the bottom than the top, but there is also a color shift. You can see it here in the grays. It isn't just a luminance shift, but at least that all seems sort of consistent. It feels like this would be closer to grayed out. Looking at these two in particular, I feel like, and the oranges, they're all sort of got the same kind of offset maybe. But anyway, they certainly seem the closest of all of these tests. And let's look at the other ones. We've got the daylight Kinoflows now versus the first of our LED daylights, and this is on the Canon again. All of these are on the Canon now. So yeah, again, big differences, and we're seeing here this worrying trend of in the daylight as well, of the fact that this Z90 seems sort of brighter in the reds, but desaturated and down in the yellows, so up in the reds, down in the yellows. I mean, it's way off in the oranges, but these skin tones, this has like a real purpley tone compared to what we'd expect from our gold standard from the Kinoflow, so a bit of a worry there. And that's about the most expensive LED we have. Going down, this is the most recent LED we bought. This is not too bad. Again, though, we've got this problem where this seems brighter in the yellows and darker in the reds, and are off in these skin tone regions, especially if you were shooting someone with African American kind of darker skin. I think you'd be getting some really weird, funky results. And if we now go to our small LED, this is the bright, this is the little LED, but it's in its daylight, so it's in its brightest form. It's not got any gel in front of it. And it's probably the best that this little one's going to perform at. I should point out, though, that while it's performing kind of better, it's certainly not right. Over here in the skin tones, it's sort of way off. Down here in the primaries, it's looking a little more like of a match, but it's certainly not. It's not outrageous, but it's not that great. But there are differences between what we're seeing in the Canon sensor and what we're seeing in the Epic sensors, which is, I think, in of itself really, really interesting. It's partly to do with these LEDs having this variable thing, and partly how those LEDs then react with the CMOS filters themselves. And it is really different between LED lighting and Kinoflow and the Arri lights. Do I hate LEDs? Absolutely not. They're a great source of light. It just proves, though, that you need to get really good LEDs and know what you're doing with them, and make sure that you test them with your individual camera. Okay, so there are differences between what's going on, and that differences really comes down to the fact that the CRI, which don't forget is like a whole level above just saying this is a daylight light. So daylight, you could say they're both daylight. You could then actually have someone certify that they've got the same CRI index. That's still not going to show you variations that can come through from these spiky emissions. You can actually see on the waveform, or rather the spectrum display here, that a Macbeth chart on an LED can come out with just some really spiky results. And a really critical part to understand this is to go back to this diagram that we saw earlier. In particular, remember I was telling you to keep an eye on this one, number 9, which was strong red, which wasn't included in the CRI. Well, we've actually got from Dito, thanks to those guys, these chart results, and this is, I think, just incredibly interesting. This is showing you how each of the lights across the top work in terms of quality for each of those colours. So just to go back, those are all the colours there, 16 of them. If you looked at the quality now, not on the overall light, but on them on an individual colour basis, you can see that on an LED flashlight, for example, you're scoring an index of 25 on bright red light, which is why, as I said earlier, you can have LEDs that maybe get recorded on camera looking green because they have an incredibly bad response to just pure red light. And as you go across the line there, you can see different lights, but even like light panels and other, very good quality lights are still not even sort of breaking a sweat above sometimes 30, 40, 50 on a value. Now, just to give you an idea, if I swap those to Kinoflows now for a second and look at the same individual light values on a Kinoflow, basically this Kinoflow, you'll see it's scoring a 98 in R9. I just want to point out one other, I guess, aside while we're here. Kinoflow actually make 3 lights. They make the daylight and the tungsten, and those are the 2 that we always talk about. They actually also make a 29, and the 29 is that one in the middle there. So if I just isolate that for you for a second. This is just a variation on the Kinoflow. They make basically the 29, the 32 and the 55, which is basically 29,000, 32,000 and 5,500. And those 3 colour temperatures, that 29 is kind of an odd case one, but it actually scores particularly badly in exactly R9 as well, which is why, I mean, I don't really have any reason to use the 29s, but I've always steered clear of them and only shot with daylight and tungsten, and that's from Kinoflow, which I think is one of the best companies in the world, if not the best, for doing fluoros. Also, if we just compare them to those original lights we looked at the very beginning of the class, which was, the HMI, sunlight, and the Dito lights, you can see that still in every respect those main normal lights. The ones that were used back in the day when they first set up the CRI, all of them score really, really well. It's only when you get the LEDs and these extra colours that we start seeing these unusual spikes. And as I say, if you look back at the LEDs, you can see just how wildly the numbers flick around. And yet, you could still get a good CRI number on a light, and you could still have a light that's rated as daylight, and somebody could sell it to you in good faith, and it just won't reproduce colours very well. And as I said at the outset and a little earlier, this all gets affected one more time at the sensor. So the tests we're doing today are to test these lights not just under these conditions, not bouncing just off these cards, but actually under those exact CMOS conditions for that last filter going into the actual chip. And just to completely finish out, I just picked up on that point about the, I think I mentioned earlier about the halogen burning out at about 3600. That's why we only run halogens at that tungsten temperature. But I just want to point out also LEDs. Now LEDs can run up to about 85, but as you get the temperature of LEDs up, the light output drops. And if you get them pushed closer to the max, you have some real problems with the colour as well. So if you're getting a good quality light, you're not going to want to run it really hot. So sometimes you'll actually see the amount of light output out of a high quality LED light, like a really good one, not being as much light output as one that's a bit cheaper. And you might think, oh, well, the cheaper one's better, right, because it's giving more light output. But if they're getting that light output by running the LEDs actually hotter, you'll get an inferior quality light. It's one of the only lights I know of that has this kind of property. It's also why, by the way, it's really hard in a studio to have LED studio lights, because if you start putting a bunch of lights up in the ceiling and you're using them with lenses, like you know, we're starting to see these at the moment, Fresnel lenses, they look like an ARRI light, but they're actually an LED light. If those suckers get hot, and they just get hot because the studio's hot and heat rises, and you start raising that ambient temperature around the LEDs from the, say, 75 that they should be running at for a professional, like an ARRI maker, I think ARRI make, but certainly Dido make a professional LED Fresnel light. If that starts pushing up just because of ambient heat to 85, you're going to kill your LEDs and kill your light quality. So what you're actually looking for is not necessarily the optimum lumens per watt when you're trying to buy a light. What you really need to buy is incredibly well-picked LEDs. I guess that's a bit of a mouthful. You need to buy a light from a manufacturer who's taken the time to select the highest quality LEDs, not just try to average it out, not just use low quality. They have to be designed so they don't run hot. And so some of the bigger Dido, for example, LED lights actually have water cooling in them to keep them cool. And you have to make sure that if you really want to get accurate about it, you actually test whatever your light setups are with your sensor. So if I was actually doing some strict tests and somebody was about to start a big project and they came up with some lights and somebody had some lighting packages that were relying on LEDs, I would actually want to do this camera test that we've been doing today now to get an idea on where we are and make sure that there was consistency across those LEDs if they're being sourced from different companies. Well, that's it for this week. I've certainly I love this kind of area of suddenly discovering things that I found to be kind of anecdotally true. For a while, I was bugged by this LED phenomenon that I was getting much better results out of stuff that was Kino flow, yet the LEDs seemed to be very popular and people were having great results with them. And some of the LEDs we got didn't have great results, and yet I knew that I was doing all the right things. And so I guess on the old principle that whatever we find really fascinating here at PhD, we figure you'll find fascinating. Hopefully you've enjoyed this week's class. Thanks so much for being with us. If you've got any questions, please fire in the forums. And that interview with Dido is coming up on FX Guide TV, where I sit down with him and just basically discuss stuff with a guy who, let's face it, has forgotten more about lighting than I'll ever know. Thanks so much for being with us. See you.